Good morning, everyone. Glad to be here today and glad to see a lot of like-minded people. My name is Dharanipathi Rathna Kumar, and I'm doing a PhD in Maynooth in Ireland. And my research topic is neural audio effects. So today's topic is going to be a bit ML focused. So I hope everybody has a decent understanding about it. Again, it's not going to be very complex. It's going to be a simple introduction kind of a thing. So let's get into it. So the topic for the day is leveraging pruning and quantization for efficient real-time audio applications. So so the first thing is neural network model compression. So it's kind of a huge field where, so anytime you train a neural network, the main focus is on improving the accuracy. People don't really give a lot of importance about the model size. The main agenda is to have a higher accuracy. And another thing is anytime you train a model, you train that in a GPU or in a GPU cluster. But then most of the times for inference, it's not going to be happening in a device that has access to computational devices like GPUs. So it might be in a CPU-based system or edge devices like phones and stuff. So this is where model compression comes in. And model compression involves techniques to reduce the size of the network without losing accuracy. And there are a couple of techniques. So weight sharing, pruning, knowledge distillation, and quantization. Today we're going to focus mainly on pruning and a bit of quantization. So I'm going to kind of focus the talk around audio plugins since I'm kind of working on neural audio plugins. So the current audio plugins are predominantly CPU dependent. So there are companies that's working on, like, for example, like GPU audio and stuff. They are trying to bring in ways where you could your plugins can use GPU for inference. And then the traditional DAWs are still the industry standard. So what I mean by that is that even though there are improvements in machine learning in audio plugin domains, but still the current DAWs doesn't really take advantage of that. So if you're building something, you need to kind of consider the existing ecosystem. And plugins within DAW typically require real-time processing. In a sense, if you load up a plugin in a track, it kind of works in real time. In a sense, the DAW sends a series of buffers and it expects a series of buffers out, and it kind of has to happen in real time. And neural network-based plugins needs to be highly efficient in order to kind of work real time. And there are few models currently available that are used in real-time neural audio effects, such as DDSP models and RAVE. But then these are the models where the architecture itself kind of inherently gives you has an advantage of running in real time. So, but if you want to use, for example, an LSTM or even a TCN that has a much larger size, it's kind of really hard to kind of do it. So this is where model compression techniques kind of comes into play. If you can train a model with a large size, but if you can kind of shrink it so that it can run in real time, that can be really helpful. So we'll look at the first technique that's called model pruning. Basically, it's a very simple technique. So all you're doing is you're pruning the model. In a sense, you're kind of shrinking the model size, but based on few criteria. So it involves identifying and removing less important neurons or connections and then retraining it most of the time to kind of improve or get back the accuracy that's been lost when you kind of shrink the model. And pruning involves applying a binary criteria to zero out weights. So what it means is that you take, for example, like let's say, we'll again cover what weight pruning or neuron pruning in a minute. But then if you want to prune a particular weight or something, you have a binary criteria in a sense. Like let's say you have a threshold. If it's above that, then it's 1. If it's below that, it's a 0. So basically you either on or you off. So also, like for example, in implementation in PyTorch, you have a mask for the model. So it'll have zeros and ones. So, and it'll kind of, and then you apply the mask on the model so that you know which weights to keep and which weights to discard. And then pruning larger networks than training, pruning larger networks after training is more effective than kind of starting with a smaller model and then kind of training. So that's kind of the idea. And then you have two types of pruning. The main two types, one would be structured pruning and one is unstructured pruning. So in structured pruning, you try to kind of prune either a filter or a neuron so that you could kind of shrink the model. So basically like let's say, or a layer. So like let's say you have a network with 3 layers, 4 layers, and if you want to prune a whole entire layer, you could kind of remove that and then have the rest of the layers combined again so that you have a smaller network. But then when you have, when you do unstructured pruning, you're basically kind of reducing the, so you're increasing the sparsity of the model. So you're not really changing the structure of the model, but you're simply making the weights more sparse. But then you could still have a bit of improvement in performance if you use sparse matrix algorithms, so where you do get a bit of advantage there. And then again, so unstructured pruning is also called like weight pruning because instead of pruning kernels, you're pruning weights. We'll again see what weights and kernels are in a minute. And then in structured pruning, you're pruning kernels or neurons. So if anybody has done a bit of machine learning and stuff, would have seen a simple architecture of a CNN. So the main idea to see, so the main points here are that, so you have a kernel. So that's going to be the one that's going to, extract some feature from your input. And then you create a feature map from that. So in essence, you'll have a feature, you'll have a filter that has multiple kernels based on the input number of input channels. And then based on your number of filters, you're going to have your number of output channels. So when you kind of do, when we work with audio, mostly we end up using 1D convolutional networks. So this is a 2D convolutional network, but then a 1D one is going to be very similar, but then instead of having a 2D kernel, you're going to have a 1D kernel, and it's going to convolve in the time axis. So in this case, since the first layer, so the input has just one channel, we are using, the filter has just one kernel. So that's kind of the idea. So you could have multiple filters and each filter will have multiple kernels, okay? So, and based on the number of kernels you have, you'll end up having, number of filters you have, you'll end up having number of features. So in this case, you technically have 3 filters, so you end up having 3 feature maps and can kind of go on. So as I said, in unstructured pruning, you simply see which weights are less significant and then you just prune those things. And in structured pruning, you kind of see which kernels or filters are less significant and then you prune that based on that. And one key thing to note is that anytime you prune a filter, you need to also make sure that, so if you prune a filter, you're going to end up having less features. And if you have less features, in the next coming layer, you need to have 1 kernel less for each filter, okay? So it's a bit hard to kind of visualize here, but just know that there's a dependency there. So when you remove one, you also remove, so when you remove one filter, you remove multiple kernels in the next layer's filters so that your model kind of, the structure stays the same. So the example I'm going to kind of show today is going to be a temporal convolution network. It's a popular network which we use in audio applications. So it's kind of an advanced form of 1D convolution. So the idea is that TCNs are causal. So in a sense, if you work with real-time audio, your model has to be causal. It can't kind of look into the future. So it needs to create, or it needs to compute each and every sample based on the current sample and the previous samples. And then to have better performance, TCNs have something called dilated convolutions. So in a sense, that helps you increase the receptive field. And also TCNs are good at parallel processing. That's one advantage it has over other sequential models like LSTM RNs and stuff. So yeah. And then this is kind of an image that kind of explains what causal and dilated convolutions are. So in this case, you could see that each kernel is of type size 2. So to generate one sample, it looks at 2 samples, but then for different layers, it has a different dilation factor. So in the first layer, you could see that it takes the kernel size is 2, but then you don't have any gaps between it. So it's like it has a dilation of 1. But then as you go, you exponentially increase the dilation so that you could achieve much larger receptive field. So for example, in this case, to compute that the rightmost sample, it can actually look at all the current and the past samples. So that's kind of the idea, and also it's causal, as I said. It's not looking into anything in the future. So this is a simple example. So in this case, I just trained a simple TCN model, and the task is to just simply emulate an low-pass filter. And if you kind of do it with an absolute mean error loss, it's going to be really easy for the model to model a low-pass filter. It can easily do it with like 1 or 2 layers with 1 or 2 channels. So so I used an STFT loss so that it's a bit hard for the model to recreate it. So in this case, this is going to be the, okay, can't load audio right now. Just 1 second. Should be fine. I think I'll just go with it. Internet is the system. I think it's fine. I'll just go with the. Anyway, I'll just explain that with the spectrogram. Still, it's pretty clear there. So that's going to be our input dry signal, and then since we wanted to kind of emulate a low-pass filter with a cutoff frequency of 100 hertz. So if you use a much smaller network that has just 8 channels, so this is a model with 3 layers, and each layer is with has 8 channels. So you don't get a very good result, as you kind of see that from the spectrogram. It does a decent job, but still you have artifacts, and it's not proper reproduction. But then when you have a 32-channel model, a larger model, but then you prune that once, and you could prune that with sparsity ratio. So in this case, I think it's 80%. So we force the model, sorry, we prune the model to kind of remove 80% of the weights. So you end up, so 80% of the filters in the 80% of the filters in each layer. So we end up having 7 channels in each of the 3 layers. So, and then we retrain it once. So we end up having a much better result. In fact, that result is kind of very similar to the 32-channel model. So as you could see that a 7-channel model performs way better than an 8-channel model since it was pruned from a much complex model. So that's kind of the idea about pruning. And then we're going to quickly have a look at quantization. So again, quantization is another technique that's been extensively used in large language models and stuff. So where the idea is to kind of reduce the precision of the parameters. It can be for the weights or biases. And then, so you basically convert. So generally, when you train a model, it's going to be in 32 float. So you convert that into 8-bit. Yeah, so you train a model with 32-bit float, and then during quantization, you convert that into 8-bit int. So as you could kind of see, the main benefits are memory usage, and then power consumption and latency. And with power consumption, as you could kind of see that an 8-bit addition is like 30 times less, consumes less energy than a 32-bit float. So, And then quantization is kind of, it's extensively used when you want to kind of deploy models to edge devices that runs on batteries and stuff. And then you have two types of quantization. One is post-training quantization, and one is quantization-aware training. Post-training quantization is very simple. You still have like dynamic and static and stuff. I'm not going to go into details of it. But in essence, it means is that you train a model and then you finally quantize it. You change the weights to a much lower precision, and also if it's dynamic quantization, then as your inputs comes in, you kind of dynamically quantize it based on the range. And then with quantization-aware training, so basically what you do is you kind of induce a fake quantization while training. In a sense, for example, an 8-bit can store 256 values. So when you train a model, you kind of, like let's say if it's a weight and if it's in 32-bit float, you kind of round it to the nearest value so that your entire range is going to have 256 values. So that's kind of the idea. But the operation still happens in floating point, but then what you do is you kind of fake quantize so that it ends up being in a rounded value. So this kind of forces the model to increase accuracy also in this constrained environment, so that you will end up having, so after training, when you actually quantize it, it's going to have much better results because it kind of has seen an environment where the values are kind of rounded to that. So again, with quantization, you might not get much improvements in terms of like audio FX plugins and stuff, but then that's something you consider it. So there are a few model compression libraries which you could use. For example, even if you use PyTorch, the problem with PyTorch is when you do structured pruning, so it'll end up giving you a mask, but you don't have, currently there's no feature in PyTorch where you could actually shrink the model just by running a couple of lines of code. But there are a few other libraries that does that. For example, neural network NNI from Microsoft. That's the one I used for the example which I showed. So where you do, you prune a model, and then once you prune, and then when you want to actually shrink it, the way it works internally is that you kind of trace the model. In a sense, you pass an input, and then you trace how the model goes, how the model, you're basically tracing it like how you draw with, tracing with a pencil. And then you kind of get the graph, and then you remove the weights or the layers, or the layers from the mask, and then you kind of stitch it again. You also have another library called torch pruning, and then you have mmRazor. So there are a few interesting neural network based audio plugin tools. I hope everyone have heard about Newton. It's really an awesome tool where if you're working on some neural network model, and if you want to kind of quickly deploy it in a DAW or something, you'd kind of use that. So that's a tool that really bridges the gap between experimenting with PyTorch and then actually using that in a DAW. And then you also have Arch Neural, where if you have something in PyTorch, you can kind of convert that into a C++ model and then use it for inference. And yeah, that's it for the day. Thanks. Any questions?
Hi, fantastic presentation. There's so much great information there. Thank you so much. I have two questions. The first one is about structured pruning. How do you select what features to tune, or what are some metrics we can use to evaluate our pruning?
So most of the time, it's going to be, in a sense, even though it's structured pruning, you're still kind of focusing on the weights, and generally they use L1 norm. So one thing I kind of mentioned to say is that pruning and regularization kind of goes hand in hand. So if you use, for example, like L1 or L2 regularization, what you do is you force the model during training to have a sparse model, so that there's going to be few weights. It's going to have value either, like if you use L1, it's going to be 0, or if you use L2, it's going to be close to 0. So that then you have a simple criteria, like an L1 norm, where you say that if a value is below a certain threshold, you just prune that. So if it's a structured pruning, then you're going to kind of have some weightage between. So either you could prune globally, or you could prune layer-wise. So let's say if it's layer-wise, you take layer, and then let's say you have 32 channels, and then based on the sparsity, sparse value you give, you take the best, the ones that has less significant weights, and then you would remove those filters.
Okay, so if you set let's say sparsity to 50%, would that be something similar to dropout?
Dropout is more like it kind of randomly drops out different weights
but
during training. You basically just zero out.
Okay.
So basically, you're kind of completely removing those.
Okay.
If it's structured, you're removing the filters, or if it's unstructured, you're removing the weights.
Okay.
Not removing in a sense, zeroing it out. Yeah.
Zeroing them out. Got it. Thank you so much. The second question is, do you see a trend where DAWs are moving towards using GPU that sort of does away with the processing power threshold and the need for pruning and quantization? Do you see that happening in the future?
I think it might be because, again, this is just my intuition. I feel that the future DAWs are going to be more web-based. So since there's going to be a lot of generative, for example, like Firefly from Adobe, so you're going to have a DAW. There's going to be everything is going to happen in their servers, so that you don't really have to worry about the processing and stuff. But still, it's going to be helpful for them if they are going to run a lot of inference and stuff. Probably something like quantization might be helpful because it's less energy, it consumes less energy and things like that. But then even if you are, I think this is more beneficial for people who are working with models, and then they want to, which are going to be helpful for audio production and stuff. And then, as I said, for example, if they want to just simply deploy that in a DAW using something like Newton, let's say you're working on LSTM, but you really want a small, there are studies that has pruned LSTMs where, you do get 3 or 4x smaller size, also 3 or 4x faster inference, Okay. So this paves way for, experiments in those architectures which you don't really normally find in real-time applications. Yeah.
Okay. Got it.
I hope that answered your question. Yeah.
It really does. Thank you so much.
Thank you. Yeah.
I would like to see a comparison of the results. I'm sure you've presented, you have it on some paper or something.
I'm yet to publish one, so probably probably in a couple of months. So it's going to be a journal paper.
Okay.
So that's going to compare not just audio plugins kind of thing. It's going to be a benchmark paper where you take existing models where you do have, so the one problem with iterative training is that, iterative pruning is that you need to kind of have the same model with the same data sets and stuff so that, once you prune something, you could train it again. So there's going to be a benchmark of models that has data set, and then models that doesn't have a data set where you just prune it, one-shot pruning without iterative training, and then you compare the results of how much reduction you do get with existing models. Yeah.
Right. For the ballpark, what is the difference in accuracy?
For example, you kind of
with and without.
So the idea is that when you normally do pruning, you try to shrink it as much as possible where you could retain the accuracy. That's kind of the idea.
I see.
So when you prune, let's say you have a model that has 100% model size and you get 100% accuracy. The idea is to keep 100% accuracy or probably go to 95 and then shrink the model as much as possible. So there are cases where you could shrink it 90%. In a sense, the model could go to just 10% of the size and still keep the 95% accuracy. Yeah.
And I can definitely see this being of a lot of importance.
Yeah.
Because there are certain projects that want to not be in the cloud and just for example, there's this speech recognition project which wants to take it to the common man, where they can talk in vernacular languages. And in instances like that, a model like this would be very helpful.
Exactly,
perhaps we could run something on board, on their device also, you know.
Yeah.
Or something that's, a small portable device.
Right.
So I see a lot of value in what you're doing.
Right. And then there's the thing called lottery ticket hypothesis. In a sense, it basically means that anytime you have a network, the assumption is that there's going to be a much smaller network that can actually, produce the same accuracy. So even with pruning, it doesn't even have to be. So the whole idea is that if you're developing some model, you could just simply try pruning once so that you could see that, hey, can I have the same accuracy at the same time reducing the model? You're not losing anything. Like you could just simply shrink it, just by doing, one or two iterative pruning. So I think whether you have a constraint or not, it's probably, I would say that it should be a standard practice where anytime you train something, you try and prune it so that if you can get a smaller network, it's beneficial. Otherwise, it's fine.
Agreed.
Yeah.
Thank you.
All right. I think that's, yep.
Hi, this is a very nice presentation. Thanks for it. I've learned a lot.
Thank you.
So with respect, when you talk about reducing the size of LLMs so that we can run, especially in the smaller devices when you was talking about.
Right.
So there are some startups which are hardware focused, like Edge.ai,
Right.
who are building the hardware that is customized to run these LLMs very efficiently.
Right.
So they're trying to move away from the whole GPU space and they're trying to build these models. So I assume that that is going to become a mainstream, at least I hope that.
Right.
So do you think even this pruning, all the things that you're trying to do to reduce the LLMs will still be valuable? Or I just wanted to understand your perspective with hardware evolution.
I think I'm not an expert in that, but still I feel that even pruning or even quantization, like mainly I think however your architecture is going to be in the hardware level, I still feel that your energy consumption is still going to be kind of the same for doing an integer calculation or a floating point calculation. So in that sense, it's not going to go away because you're still going to get that benefit. Also with models, like it's just that, as I said, you're not really losing anything. You're going to keep the accuracy at the same time, just shrinking it. So anything you get is kind of a free lunch. They do call it free lunch. So yeah.
Right. So, but the only thing is now, if you talk about say 100% size to 10%, it sounds amazing. Right. Now there'll be a lot of interest.
Yeah.
But the moment the hardware is going to take that, maybe we might not be able to see that big a difference is what I was feeling, but maybe I was wrong. So we have more.
Yeah, exactly. Yeah. If your infrastructure is, if you have a limited infrastructure, as you said, like you could have more models running. Yeah. It's always going to be some efficiency there. So yeah.
Cool.
But again, I'm not sure about there's going to be any special hardware that's going to come up for audio specific thing, as you said.
Yeah.
Since there's a lot of investment in LLMs, is because that's where the money is. But hopefully,
But it'll work because it's fundamentally it's it's a neural network, right? So you have the same nodes and weights.
Like let's say they make some hardware that's very specific for transformers. Something that does something.
Right.
That improves something where there's attention or something like that. Then I'm not sure how that's going to be beneficial. Again,
sure.
I'm not an expert in that, but I just feel that way. Yeah.
Sure. Yeah. Thanks.
Hello. Yeah, one quick question. So at least to me, when I'm looking at quantization, it looks like, at least on paper and with the example that you gave, that it would be a very, very big impact on accuracy there. Like going from F32 to int8.
Right.
It sounds like the impact on accuracy would be substantial. So how do you, I don't know.
So that's where, so when you do just quantization after, post-training quantization, you're not going to get that benefit much. But then when you do quantization aware training, where you do consider that, so you do get benefits there. In a sense, it can actually perform better. Like studies kind of show that. So they do. There's the term called quantization noise. Of course, there's going to be some loss in accuracy, but the trade-off is you're like reducing it way too much, but at the same time, your accuracy is not going to drop similarly. So your loss in accuracy is going to be much minimal compared to, the amount of reduction you have in the precision. That's kind of the idea, yeah. There are research where 1-bit, 2-bit, 3-bit LLM models and stuff, it might sound like, how can you do that in 1-bit? But still, that's a very cutting edge research that's happening. And it's there, it does work, so yeah.
And I'm assuming, you can probably combine both pruning and quantization.
Yes, exactly, yeah. Anytime you do, yeah, of course. But as I said, when you're like doing something like an audio effects, a neural audio effect, probably quantization might be kind of an overkill with the latency and stuff. at least my research currently is more focused on pruning. But again, quantization can also be, also this thing called knowledge distillation, where you have a teacher-student network, so you train a larger network and then that's going to be a teacher network that's going to train a smaller network, a student network. So there are other techniques which they use for model compression, and these two are one major things, yeah. Thank you. Yeah. Thank you, everyone.